Hi everyone, and thank you for attending today's webinar, AI for Makers, Learn with JetBot, hosted by John Welsh. Before we begin, we wanted to cover a few housekeeping items. At the bottom of your screen are multiple application widgets. All of the widgets, as well as the slide area, are resizable and movable, so feel free to move them around to get the most out of your desktop space. If you have any questions during the webinar, please submit them through the Q&A widget. We'll try to cover as many questions as possible during the Q&A portion, but if there's any we don't get to, please post them on the forum to keep the conversation going. Be sure to check out the resource list for links to the developer site, forums, wiki, and more. And if you run into any technical issues during the webinar, you can find answers to some common questions located in the Help widget at the bottom of your screen. An on-demand version of the webinar, as well as the slide deck, will be emailed to you later today. And with that, let's get started.
Hello everyone, my name is John Welsh and I'll be presenting today's webinar titled AI for Makers, Learn with JetBot. Before we get started, I want to give a brief introduction to who I am and what I do at NVIDIA. My title at NVIDIA is Developer Technology Engineer. What that means is I focus on applications of NVIDIA Jetson, typically using deep learning. It also means that I create open source software and content that enables other developers to create things using NVIDIA Jetson. Before joining NVIDIA, I was introduced to deep learning during my master's thesis, where I used deep learning for pose recognition to enable a robot to more reliably follow a person. My knowledge of deep learning has been helpful in creating projects like JetBot, which we built here at NVIDIA to show people how to get started with Jetson Nano. JetBot is open source and comes with the full bill of materials needed to create the robot from scratch. It also has a hardware setup guide with pictures and instructions so that you can build it yourself. The examples in JetBot will take you through the basics, like using Python to program from your web browser, and controlling basic motions of the robot, to full AI workflows where you'll teach JetBot how to avoid collisions. We hope that by building JetBot and running through the examples, you'll feel more comfortable with Jetson Nano and how to apply AI to new problems. Like how we applied the JetBot road following sample to this RC car, or like the NVIDIA Green Machine that our interns built last summer using the Jetson TX2. We think that there's a class of projects that Jetson Nano is particularly well suited for. These projects usually include low latency camera input, real-time processing using deep learning on the NVIDIA Jetson's combined CPU-GPU architecture, and hardware interfacing, either using the USB ports or the GPIO pins provided on the Jetson Nano developer kit. We hope to teach you how to create projects with Jetson Nano by running through JetBot. So the way we'll structure this webinar is we'll first cover the hardware that we used in JetBot, where you can discover components that will be useful for your own projects. We'll then run through the software setup, including how to create an SD card from scratch, so that you'll learn how to structure your project to be reproducible. And then we'll run through the examples, where you'll learn how to apply AI to new problems, which will be useful for creating your own projects. So let's get started by going through the hardware of JetBot, and we'll focus on the pieces that will be useful for creating your own projects. The hardware in JetBot can be accessed by navigating to github.com/NVIDIA-AI-IoT/JetBot. If you navigate to the Wiki tab, you'll find the bill of materials in the homepage of the wiki. Under Common Components, you'll see a list of hardware that is needed for each JetBot that you want to build. For each JetBot, you'll need to order the number listed under the quantity column. Perhaps obvious, but the most essential component you'll need when building JetBot is an NVIDIA Jetson Nano. You can purchase this by clicking the link under the URL column. This will take you to the NVIDIA webpage, where you can buy directly from NVIDIA, or if you hit Buy Now, where you'll see a list of third-party vendors like Arrow, Amazon, Seed, SparkFun, and Newegg, which sell the development kit as well. The next item is the microSD card, for which we list a size of 64 gigabytes. You can purchase it from Amazon at the link listed. The reason we use a 64 gigabyte SD card is to allow plenty of space to store data when you're collecting your data set with JetBot. You could probably also get away with a 32 gigabyte SD card. For JetBot, we wouldn't recommend a 16 gigabyte SD card, because you may not be able to comfortably store the dataset and install additional software on top of our SD card image. When using an SD card smaller than 64 gigabytes, you may need to follow the Create SD Card from scratch under the wiki, which we'll cover later in this webinar. The next item in the bill of materials is the micro USB power supply. You can purchase the power supply from Adafruit. This is also the power supply that's recommended in the Getting Started with Jetson Nano guide. It's important that the power supply that you use over micro USB can supply 5 volts at 2 amps. Even with the appropriate micro USB power supply, it's possible that the Jetson Nano can draw more power than can be consumed over the micro USB port. To remedy this and run the Jetson Nano at lower power consumption, you can use a tool called NVP model. In a terminal, we can set the Jetson Nano to 5 watt mode by typing sudo NVP model-M1. To check the current power mode of the Jetson Nano, we can type sudo NVP model-Q. We can see that the Jetson Nano is in 5 watt mode. To configure the Jetson Nano to run back in 10 watt mode, we can type sudo NVP model-M0. Instead of reducing the power consumption of the Jetson Nano using NVP model, we could also provide more power to the Jetson Nano development kit using some other options. These options include powering at 5 volts 4 amps over the barrel plug adapter, or by powering at 5 volts 6 amps using 2 of the 3 amp pins on the GPIO header, or, as mentioned earlier, powering at 5 volts 2 amps over micro USB. For JetBot, we're powering over the micro USB port because of the simplicity, but for your project, depending on the power consumption, you might want to use one of the other options. The power supply that we list in JetBot can be used to power the Jetson Nano directly, but we also use it to charge the battery pack. The battery we list in the bill of materials is a consumer battery pack that's typically used to charge mobile devices. We selected a consumer battery pack because it's cheap and it has the charging circuitry built in. But these battery packs often have caveats, so it's important to test the battery pack for your application. We tested this battery pack with the full JetBot configuration through all the examples to make sure that it could supply enough power for the components. The next notable item on the bill of materials is the motor driver. The motor driver that we selected from Adafruit takes commands over I2C pins on the GPIO header, generates a PWM signal, which is used to drive an H-bridge and ultimately control the motors. It was especially easy to control these motors with software given the new NVIDIA Jetson support for the I2C and GPIO portions of the Adafruit Blinka library. This support allows us to use Python libraries like the Adafruit MotorKit library, which makes it very easy to control motors. This also allows us to use various other sensors that are supported by Adafruit Blinka I2C and GPIO. Other hardware distributors like Seed Studio have also announced support for NVIDIA Jetson Nano, which allows us to use various of their Grove peripherals with Jetson Nano. These features make it much easier to incorporate hardware into your AI projects. For example, we could use the Pi OLED display from Adafruit in Python without having to write our own driver. The next notable items on the bill of material are the 3D printed chassis and camera mount. We provide some tips on how to obtain these components in a separate page titled 3D Printing on the wiki. If you don't have a 3D printer, it's possible that you could use a printing service to print the chassis and then mail it. The next notable item on the bill of materials is the camera. We choose a wide field of view camera option for JetBot so that it can see the ground immediately below it to detect obstacles and features, as well as see slightly above the horizon in case it needs to track an object. We restricted the camera placement of JetBot to improve the generalizability of neural networks trained for JetBot across different robots. That said, because we wanted to showcase different camera options that you can use with NVIDIA Jetson Nano and make the JetBot project more accessible in case an item's out of stock, we list two options for the camera. One option is the Leopard Imaging H145 camera, and another option is the Raspberry Pi V2 camera module combined with a wide-angle attachment lens. The field of view of the cameras are slightly different, so it's possible that a neural network trained on one camera won't generalize as well when used on a different camera. However, as we'll learn later in the examples, it's very easy to collect your own dataset and train a neural network yourself. This will be a very useful skill when creating your own projects because you might want to do something other than the collision avoidance example that we're doing with JetBot. When you're picking a camera for your project, an important feature to look for is whether it has a driver on for NVIDIA Jetson. The Sony IMX219 sensor does have drivers, so most cameras with this sensor and the appropriate connector will work with Jetson Nano. For example, ArduCam offers various camera boards based on this sensor that have the correct connector and also allow for a custom lens selection using either an M12 or CS lens mount. They also provide a comprehensive lens kit with fields of view ranging from 10 to 200 degrees that you could use to prototype your projects. The final item that we'll cover on the bill of materials that we think will be useful for your own projects is the Wi-Fi solution. Similar to how we offer two options for cameras, we also offer two options for Wi-Fi. One option is to get an M2 dual-band wireless card along with a pair of U.FL connector antennas. The other option is to get a USB Wi-Fi dongle. It's important to ensure that the Wi-Fi solution you choose has drivers for NVIDIA Jetson. Both of the options that we list on the JetBot bill of materials do have drivers, so these are good options to choose when you're building your own project. For the JetBot project, we recommend the first option, which is the M2 card and antennas, because we have the most experience applying this with the full system configuration. That concludes our discussion on the hardware components of JetBot. You can build JetBot by following the hardware setup guide in the wiki on GitHub. Now, let's talk about the software components of JetBot, like how to install TensorFlow and PyTorch and create a custom SD card for your project. Before we go through the steps of how to install the JetBot software, let's talk about how the JetBot project's organized. JetBot's hosted on GitHub. As a repository, there's a selection of files and folders that are versioned. An important file in the project is the setup.py file. This will call scripts to build and package our project so that we can import it in Python without having to configure the path. Under the JetBot folder, we can see different software components like a camera class, motor class, and some other utilities that we found common throughout the JetBot examples, so we wanted to make the abstractions. If you dig into the code, you can learn more about how we structured the project and use libraries like OpenCV to capture video from the camera. In the Notebooks folder, you'll see different examples organized by name. If we navigate into one of the examples, we'll see the set of IPython notebooks, broken into their different stages. The reason we have 3 separate notebooks for the collision avoidance example is in case you wanted to train the model on a device other than the NVIDIA Jetson Nano. We put the documentation and content that wasn't as important to be versioned in the wiki so that we could easily adjust it and make it fit our needs. We found it important in the documentation to have all the components that someone visiting the repository would need in order to recreate what we've done and learn from it. While the most important thing when building your AI project is to have fun and do something that interests you, There's an opportunity for others to learn from your work if you include the necessary information for them to understand what your project's about and how to reproduce it. One way to make your AI project more easily reproducible is to create a custom SD card image. You can pre-configure the SD card image with all the necessary software and system configurations so that when you want to use your project elsewhere, or you want others to use your projects, you don't have to run through all these tedious steps. As always, make sure you're compliant with the licenses of the software that you're using. This is what we did for the JetBot project, so all anyone has to do is download our compressed SD card image, flash it onto the SD card, plug it into the Jetson Nano, and then boot up. So let's show how you can create your own SD card image from scratch. To create the JetBot SD card image, we start from the SD card image mentioned in the Getting Started with Jetson Nano Developer Kit guide. Following the instructions in the Getting Started guide, we flash the SD card image using a tool for either Windows, Mac, or Linux. We then plug the SD card image into our Jetson Nano Developer Kit and boot up. The first time you boot from the standard SD card image mentioned in the Getting Started guide, you need to configure the Linux operating system with a username and password. For the JetBot project, we set this to JetBot and JetBot. And we also select to log in automatically so that we'll automatically connect to Wi-Fi when we turn on the robot. We then install various software dependencies. One of the first ones we need to install is pip for Python 3, which is a package installer for Python. We do this in a terminal on the Jetson Nano by typing sudo apt-get install python 3 pip. NVIDIA provides an official pre-built TensorFlow pip wheel that has instructions at the link shown. If you can follow these instructions on the Jetson Nano from a terminal, like we did to install the pip package, you'll be able to use TensorFlow from Python. The next notable package that we install for JetBot that we think will be very useful for your projects is PyTorch. On our developer forums, we posted pre-built PyTorch pip wheels for Python 2.7 and Python 3.6. If you copy the commands listed under the version you want to use into a terminal on the Jetson Nano, you can easily install the PyTorch pip wheel and then begin using it in Python. One feature of JetBot that we find that people are particularly interested in is that it's programmed from a web browser using JupyterLab. In our Create SD card image from scratch, we list the steps necessary in order to install JupyterLab and configure a password on the Jetson Nano. By default, if you wanted to use JupyterLab, you would need to launch the service manually every time that you'd boot the Jetson Nano. You would do this by typing the following command. However, we wanted it to be much more convenient by allowing the JupyterLab service to start immediately when the Jetson Nano booted, as well as a service that would display the IP address, so that all you need to do to program the robot is read the IP address and then connect to that IP address on your browser. We provide the scripts to generate these services as part of the JetBot Python package, so all you need to do is clone and install the JetBot package, and then execute the scripts and enable the system services, and then enable the system services so that the JupyterLab server and the stats display script will start at boot. As a final step, we create a 4 GB swap file that's enabled at boot so that runtime memory that's accessed less frequently can be placed on permanent storage. Once you have your Jetson Nano configured just how you want it, you can create a snapshot of the SD card image that you can compress to use in other copies of your project or so other users can easily use your project. To do this, you would first shut down the Jetson Nano and remove the SD card from the SD card slot. Then, you would plug the SD card into a Linux desktop machine and check where the device is located by typing sudo fdisk-l. Assuming the SD card is located at dev/sdb, we could record a snapshot of the SD card image to a file by typing the following command. To greatly reduce the size of this file, we would then compress it using the tool zip by typing the following. This new compressed image that we just created could be used just like the SD card image in the Getting Started with Jetson Nano Developer Kit guide using the tool Etcher. This tool is able to accept the compressed image directly. That concludes our discussion on how the JetBot project is structured and how you can structure your own project to be more reproducible. The content that we've covered in this webinar so far shouldn't be so unfamiliar if you're working with Raspberry Pi. Now we'll get into the area where NVIDIA Jetson really excels, which is real-time deep learning, and we'll explore these concepts through the examples provided in JetBot. The examples in JetBot are in the form of Jupyter notebooks that you can access by connecting to the robot from your web browser. After you've followed the initial setup and power on your JetBot, the IP address will automatically be displayed on the PIO LED screen when the JetBot boots up. We enter this IP address in our web browser with the port 8888. We're presented with the notebooks folder that we mentioned earlier in the GitHub repository. We've copied them into a folder titled Notebooks just to be slightly more convenient. And we're also presented with the first example notebook called Basic Motion. The Basic Motion notebook will help you get familiarized with the Jupyter Notebook environment, like how you can execute code to call different commands, like how we call left here, use widgets to control different parameters of the robot. The next example in the series is the teleoperation example, where you'll use a gamepad controller connected to your host computer. The gamepad is accessed through the web browser using HTML5. In this example, you'll also learn how to preview live video from the robot within the Jupyter Notebook itself using consecutive compressed JPEG frames. The next example in the series is the collision avoidance example. This example is broken into 3 parts. Data collection, where we'll collect a classification data set to tell whether there's an imminent collision or whether the robot is safe to move forward. We'll then train the model with the train model notebook, and then we'll deploy the model for a live demo where the robot will move around and turn if it thinks it's unable to move forward. So let's get started with the data collection notebook. In this notebook, the first thing we do is display the live camera feed. We set the camera to capture at a width and height of 224 pixels because this is what will be fed into the neural network. You could capture at higher resolution and then downsample later in case you wanted to experiment with different neural network input sizes, but most of the neural networks that we'll be using for classification default to 224 by 224 pixels, and from our tests this is sufficient for the task at hand. But we do encourage you to explore different options and try new things out to see how you can trade off between performance and accuracy. The next block of code will create a dataset folder that we can see in the Jupyter file browser on the left. If we navigate into the dataset folder, we'll see 2 directories named blocked and free. These will store the images of each class. The blocked folder will contain images of instances where the robot is unable to move forward, and the free folder will contain images of instances where the robot can move forward. The following blocks of code will create widgets that we can use as buttons to save images to each class folder. And then we attach functions to actually perform this operation to the widgets. We then display all the widgets together for convenience. We'll now go ahead and collect our data set. When collecting our data set, it's important to get a good amount of data, but even more important is the variety of the data. We want to show different scenarios that the robot could be blocked, like a ledge, or an object like my cell phone, maybe a cable in front of it on the ground, the corner of my laptop, maybe the corner of my laptop at a different angle, and then we want to show different instances when it's free, like basically just different angles away from the object region. So now we'll go ahead and collect a data set using my desk as a training environment. We'll see how well the model performs on my desk as well as environments that weren't in the training set. I've finished collecting about 100 images of each class, and it took a total of 5 minutes. We can see the images by navigating using the Jupyter Lab file browser. Let's go ahead and open up the training notebook. Before we begin the training notebook, I'm going to shut down my JetBot and power it directly with the power adapter. Now I have opened the training notebook. In the training notebook, we'll use PyTorch to define and train our neural network. The PyTorch library provides some utilities for loading data. For example, there's an image folder class, which is able to accept data in the format that we stored it in. It also allows us to apply transformations, like randomly adjusting the hue and brightness, which can help improve the generalizability of our model. It's also possible to create your own dataset implementation that could accept datasets in formats other than this image folder format. We'll do this in our road following example, where we create a custom dataset that loads images along with XY coordinates of a target in the image. Because our custom dataset class implements the torch dataset, length, and getItem methods, we can use it with the torch data utilities like this random split function and the data loader, which produces batches of samples and allows shuffling as well as multi-threaded loading. After we've defined our dataset, we'll define our neural network. The model that we'll be using is called AlexNet, and we'll start from a pre-trained model that was trained on the ImageNet dataset. The reason we start from a pre-trained model is that the neural network has already learned important features of natural images like textures and edges that will be useful in accelerating the training of our own model. It also can improve generalizability because these features were learned over many more images than our dataset will have. The AlexNet model that we'll be using is defined in the Torch Vision package. You can see its implementation here. It's defined as a PyTorch module, and the pre-trained weights are stored at this path. In our implementation, we'll replace the final matrix multiplication with a matrix multiplication that has an output dimension of 2. The reason we do this is that the original model was defined for 1,000 classes, while we only have 2 classes, blocked and free. The Torch Vision package also has other neural network architectures that span the spectrum of computational complexity and accuracy. In our road following example, we'll use ResNet 18 and show how you can modify a layer in this network to work with the output dimension that you want. We also hope to soon show in this project how you can accelerate many of these model architectures using NVIDIA TensorRT to get faster inference speeds on the Jetson Nano. The last notable item in the training notebook that I want to mention is the PyTorch optimizer. For this example, we're using stochastic gradient descent, and we're optimizing over all of the parameters in the network. The stochastic gradient descent optimizer takes a few parameters, like the learning rate and the momentum. You could adjust these parameters to change how the neural network converges during training. Another thing you could adjust is which parameters that you want to optimize over. For example, if we wanted to optimize over just the final layer in the neural network, we could do this. Let's go ahead and run the training loop. This will optimize a loss value that's computed using our predicted outputs and the true outputs. This loop will also test against our test dataset split. We can create a new window for the output of this code cell by right-clicking and select Create New View for Output. This will display the history of our test accuracy over each epoch during training. It took about 5 minutes to run 15 epochs over our entire dataset, and the final model is stored in the Jupyter file browser to the left. As the complexity of your dataset or your neural network architecture increases, you might need to consider using a desktop GPU machine or cloud GPU machine for faster training. Let's see how our neural network performs. To do this, we open up the live demo notebook. Now we have our live demo notebook open, and we can see the live video feed from the robot, as well as a slider indicating the probability that the robot thinks that it's blocked. Let's go ahead and see how the robot responds to different situations on my desk. As you can see, it did pretty well. But when I put the robot on a different surface, like this more textured hardwood floor surface, it's a little more confused, likely because our training set only included one surface. It's also very confused on this cloth surface, given the textures. I'm going to go ahead and collect different data sets on these different surfaces to see how well the robot does when we add new data into the mix. I'll keep my data sets disjoint so that I can evaluate how well a neural network trained under different sets of data generalizes to sets of data that aren't in the training set. It took me about 5 minutes per dataset to collect the other two datasets, which also have about 100 images per class. I now have 3 datasets in the file browser to the left: dataset bed, dataset desk, and dataset floor. I'm going to go ahead and train 4 different neural networks. 3 of them will be trained on each dataset independently, and then 1 will be trained on all 3 datasets at once. I'll then test the accuracy of each neural network against each situation as well. Now that I've finished training, you can see this matrix which shows the accuracy of the 5 different models that we trained against each 3 test scenarios. It's important to note our test and trained datasets are completely disjoint. In no scenario are we using an image that we trained on for evaluation. We can see that the bed dataset generalizes the best across the different test sets, possibly due to the more varied surface complexion of the cloth. Unsurprisingly, training on all 3 datasets combined resulted in the highest accuracy, and it actually improved the ability in some scenarios for the model to generalize better within its own environment. By selecting a random subset of all 3 training sets combined, we have this dataset that's labeled all. This model is trained on the same amount of images as the other datasets, so that we're not biasing by the number of images we're using. As you can see, this model, even though it was trained with the same number of images, is able to generalize much better across environments than a model trained on any environment in particular. But you can see it has slightly lower accuracy within any environment in particular. Now let's go ahead and take our best model trained on 300 images and try it out in a live demo to see how it does. I found that the features available in Jetson Nano were crucial in being able to rapidly prototype JetBot. Having the Ubuntu 18.04 desktop environment made it easy to install software like Jupyter Lab, which was critical for prototyping my applications. It was also nice to be able to select from a variety of deep learning frameworks to pick the one that suited the project's need. The availability of the Sony IMX219 driver gave me a wide selection of affordable cameras to choose from. And the support for various Python hardware libraries made it easy to integrate hardware into my project. The performance of the Jetson Nano made it possible to do real-time inference, which is necessary for real-time projects like JetBot. And finally, it's valuable to know that as my project scales up, with more data, more image streams, larger neural network architectures, or higher resolution inputs, that there's a scaling path across Jetsons, and I don't need to change much of the software. That concludes this presentation. And if you're new to AI, I hope you see how accessible it really is. That with a $99 platform, you can begin learning and incorporating AI into your projects. To learn more about JetBot, like how we did real-time object detection, or our upcoming road following example, check out the JetBot GitHub page. If you're familiar with robotics operating system, we also have a JetBot ROS port, which has useful components for integrating JetBot with ROS. Thanks for your time, and I look forward to seeing what kind of
Hi, everyone. This is John. Hopefully you enjoyed the webinar. We got a lot of questions that came in, so I'm going to try to cover as many of them as I can, as much detail as I can. One of the first questions we got in the webinar was how to choose which power mode that you want to run the Jetson in. You saw the command, so you can use NVP model to select 10-watt mode or 5-watt mode. You can also come up with your own configuration. So it's very flexible in being able to trade off between the performance and power consumption. So I think it really depends on your application. So for JetBot, we're powering over the 5-volt 2-amp micro USB power supply, and we have limitations on how much current the battery can power. So we sometimes set it to 5-watt mode, especially if you have different peripherals attached over USB. That might be necessary so that you don't draw more power than the battery can consume. And also, it depends on the latency you need in your application. If you don't need it to run super fast, you could tune down the power and save some energy. So it really depends on the application. But anyways, you can trade off between the power consumption pretty easily. So the next question that I got was, do I train the neural network on a PC and then transfer the trained model to the Nano? And it's a really good question because it kind of depends. So basically, for the collision avoidance example that you saw, I did it entirely on the Nano. But obviously, I'm limited by how large of a batch I can train on. And the more data I have, which, as you saw, means the more accurate the model will be, the longer it's going to take to train. So you can get started on a Nano, and you can collect a data set for something like image classification using transfer learning. But as you get more and more data, you're probably going to need to scale up to like a GPU desktop or a GPU cloud instance. We saw a lot of questions also about the ArduCam lens kit. And so the lens kit that I showed, they're all using an M12 mount, and I think they have different adapters to change the height of that the lens can be mounted away from the sensor. So as far as I know, I think you have to use the ArduCam IMX219 camera board with an M12 lens mount, and then you should be able to use the lens kit and try out different fields of view, because maybe you don't know exactly what you want to use for your project because we're not sure exactly where you're going to put your project. So it's a good way to play around with different fields of view and figure out what works for your application. So another question we got, or a comment, was that if there are alternative projects that you can get started with Jetson Nano with in case you don't want to do the full JetBot. And right now we have JetBot. We made that, and so it's $150 in addition to the Jetson Nano. But you can definitely get started with Nano without having a whole JetBot, and you can use just parts of the JetBot if you want. I hope the first section in this kind of gave you an idea of what hardware is compatible with Jetson Nano. So like the cameras and a battery pack that works. So if you wanted to just get started with real-time deep inference on the Jetson Nano, you could probably just get away with a camera in the Jetson Nano itself and maybe not even do the web programming. It gets more convenient when you have a battery and then you have the Wi-Fi and the IP display, because then it's portable, which fun for playing around and testing things. But you can definitely get started with just the camera and the Jetson Nano. And then the hope is that you can eventually, you guys will start to post your own projects, and other people can learn from that and get inspired and recreate what you've done. So that's kind of the hope. So, but yeah, right now we have JetBot, but hopefully we'll see more projects emerge and more stuff come out that you guys can reproduce. Another question we got is if you can run JetBot software on a TX2. The TX2 consumes a bit more power than the Jetson Nano, and the development kit for TX2 is larger, so you wouldn't probably be able to use the same form factor as JetBot, but the software, at least the deep learning components, are almost entirely in PyTorch. So that will run on the TX2 as well because they have the same underlying software stack. And even a lot of the drivers and the GPIO headers are supported across the entire Jetson platform suite. So a lot of the software you can pull from and use on the TX2. I think there's some aspects that wouldn't just work right out of the box, but it's definitely doable and it's not too hard because there's a lot of Python libraries in there to make things a lot easier. Another question that I got was, is TRT for training, TensorRT, which is our accelerator for inference, for training, isn't it for inference? Yes, it's for inference. So maybe I misspoke somewhere in the webinar, but TensorRT is for inference. So what you would do is you train your model in a framework like PyTorch, and then once your model's trained, you convert it to TensorRT, and then you run the TensorRT optimizer, and that will basically do stuff like fusing layers and a bunch of stuff to accelerate your model for inference so that you can get usually like 2 to 4 times speed up when you're just trying to run the model after you've already trained it. So hopefully we'll be able to document that more in the JetBot project. We're definitely looking into that so that you can really get the most out of the Jetson Nano where you need the performance. So, interesting question I got too was about a group working on a robot to follow a person, and they want to track the human in front of the robot. So what's the best way to do this? I spent a little bit of time on this problem, and there's a lot of aspects of it. So I think it depends, in what scenarios and what reliability you want to follow the person. So one of the hard things about following a person is if the person goes out of the scene or they're occluded, how do you recognize them again, especially because their face might not be showing? So the way I kind of worked on this was using a technique called person re-identification, and there's some data sets out there. So you would basically detect all the people in the images, and then you'd select each person, and you come up with basically an identity based off their general appearance, and that could be including their clothes. So then combine this with something like face recognition, and you have 2 metrics for being able to sort of recognize a person and follow them. So if you're really trying to do the re-identification, that's kind of one way you could approach it. But it's also, if you think about how the robot will interact with a person, maybe it's good enough like we did in the JetBot project just to follow the person closest to the center of the field of view, and then the robot tracking that person will kind of naturally follow it. And then if they get occluded, the person would have to step in and have the robot start following it again. So 2 kind of ways to do it. Look and see which other question. Another question we got is if there's OpenCV in the JetBot image. And yes, there is. There's actually OpenCV in the standard Jetson Nano image that's in the Getting Started guide. So we use OpenCV. It's compiled with GStreamer support. If you're not familiar with GStreamer, it's a way to create kind of like multimedia pipelines. So what this lets us do is it lets us acquire images from the camera using the NVIDIA Jetson's ISP, and that's an image signal processor. So it's a really fast way to access data and format it if you're acquiring it from a CSI camera. So yes, we have OpenCV, and yes, the OpenCV supports GStreamer. So yes, you get accelerated camera acquisition, which is primarily what I use it for, and then feed that into a deep learning pipeline. So another question is, what FPS can we get for recognizing objects? And with the models, so in JetBot, we have 2 TensorRT accelerated models, and that run at, I think, 14 FPS for MobileNet V2 and 18 FPS for SSD MobileNet V1. And the nice thing about these models is that you can use the TensorFlow object detection API to train them for your own tasks. So if you make your own data set with a bunch of bounding boxes, you could train it on there, and then you'd have to use one of those models for the tools that we have in the JetBot project. But if you use one of those model architectures, then you could train it to detect whatever bounding box you want, and then you can get basically 14 or 18 FPS depending on which model you're using on the Jetson Nano. So another question is if the robot can recognize hand signals, like raising your hand to stop the robot, or point to change the direction of the robot. And that's a really cool question, because I think gesture interaction is an area where Jetson Nano could really excel. And out of the box, the answer is it doesn't have that capability, but the longer term answer is that it's probably definitely possible. So there's a few ways you could approach this. Hand signals, one is pose recognition. So there's lots of pre-trained models for pose recognition. I think there's actually some videos already online of people running OpenPose on Jetson Nano. So I would check that out. But you could use out-of-the-box pose recognition, or you could even train something to recognize whatever gesture you want yourself. So if you took a bunch of pictures of yourself standing in one position, and then took a bunch of pictures standing in a different position, it could potentially differentiate between the two as a very, very simple way to detect a gesture. And also, while we're on that, so that would be one way to do it, using image classification. But if you saw the snippets we included, we have a road following example coming out soon. And what this is actually doing is regression. So it has an image as an input, and rather than determining a class label, like blocked or free, like you saw, it's actually going to determine 2 values, which are X and Y. And these are the coordinates of some target that we're going to label in the image. So for road following, what we're doing is we're labeling, basically, we'll explain it in more detail when we publish the example, but we're basically explaining the direction we want the robot to travel. And how we define that is a little more involved, but in general, we're just pointing in the image where we want the robot to go, and it's going there. So that exact code, instead of saying have the robot go to this coordinate, you can instead maybe label your nose if you wanted to track your nose, or your wrist if you wanted to track your wrist, or something like that. And right now, this example would only work with one point you're trying to track, but the fact that you can create your own data set, label it yourself, train it yourself, and it doesn't require that much data to do, is really powerful, because you'll be able to incorporate in that in a lot of projects, I think. It's depending on how creative you get, basically. One question we got is that they noticed everything is done in Python. Are other languages recommended as well, such as Java? And So I'm personally, for robotics, I primarily use Python, C, and C++. JetBot, we chose Python because it's a really flexible and fast language to prototype in, which we think when you're experimenting with projects and you're trying to create something really fast, you want that flexibility. And it also probably has the widest support for deep learning frameworks. So TensorFlow and PyTorch are both have Python APIs that are really comprehensive, and you can take advantage of all of the scripting utilities that are available and other libraries like the OpenCV Python library. So I'm most familiar with Python, C, and C++, and I think these are the most popular in the robotics community. So that's kind of why we did that. But you could definitely play around with trying out different languages. So another question we got is if you need to do PID control for the motors and moving of JetBot. And I think that depends on what you're trying to do. So for our object tracking, we just do proportional. And so if you're not familiar with PID control, it's basically just a way to control some actuators to achieve some goal. So for our object tracking or our road following examples, we would use this to either track the center of the road or to track a target object we're trying to do so that it turns out to be really smooth. So, I mean, you could do whatever you want. You could try something like move forward if target is within this region, and then turn right if it's out of it. And then try out adding proportional control to see if it makes it any smoother. So in general, I'd recommend just to start simple. Think about what your task needs. Like for our collision avoidance, it's really just going forward, and then when it doesn't see an obstacle, it turns left. So all the complexities basically in the deep learning there. So you can start simple and then figure out what you need and go from there. So another question we got is, what is integration with the ROS? So if you're not familiar with ROS, it's Robot Operating System, and it's basically a framework and tool set for building pretty extensive robotics applications. So we made a port of JetBot for ROS that will allow you to control the motors and access the camera using ROS nodes. So if you're familiar with ROS and you just want to play around with JetBot and ROS, that's a great tool to have. But for our Python libraries, we're not actually using ROS under the hood. It's all done in just plain old Python using kind of the maker libraries from Adafruit and that kind of thing. Can I see a video? So the next question that I saw is, how can I see a video of where the object recognition works? And you can go to the JetBot GitHub, head over to the examples, and then there's a video of a demo. And then if you search TensorFlow Object Detection API, you'll find more information about how to train the object detection model. And I actually, the last tutorial I did covered this exactly. So if you search our tutorials, you can find one on TensorFlow and TensorRT, and it'll talk about how you can train an object detector and accelerate it with TensorRT. Okay. So another question we got was if there's any applications that we might suggest for a design project at a university, like in computer science or computer engineering. And I think JetBot's a cool example. I actually have a bit of an education background working in robotics in a college curriculum. So a lot of that knowledge actually sort of went into the JetBot project and thinking about how it could be educational and what people could take away from it, as well as the practical needs of kind of a college curriculum. So JetBot itself wouldn't be a bad thing if you can find a way to build it. So it would make it a lot easier if you have a 3D printer. So JetBot, and then you can also start with, as I mentioned earlier, just the camera and a Nano, and you can run a lot of the deep learning samples to get people started learning deep learning, training a model, collecting data on a small scale. But the nice part is it's really flexible and accessible. So as far as like a specific application, I think it depends what you're trying to teach and what you want the students to learn. But you can definitely use Jetson Nano to get started with teaching AI in general. And also, I think having the live camera is a really exciting aspect because it's nice to interact with it and see how it does in the real world. Another question we got is how compatible is Jetson Nano with I think this is Intel RealSense depth camera. So there are already YouTube videos online about how to integrate the Intel RealSense camera with Jetson Nano. I think they're from Jetson Hacks. And so the camera works on Nano. As far as JetBot, our software is all targeting monocular camera. Because our focus is on using deep learning, and most pre-trained models that you would use, and most of the theory there is all based around single images, or not theory, but most of the research there is based around single images. So we wanted to transfer that and apply it. So that's why we choose monocular camera for JetBot. That said, the camera mount can be removed, so it's modular. So you could 3D print your own camera mount for the Intel RealSense, plug it in over USB. You know it'll work with the Jetson Nano. And then depending on what you're trying to do, you could go from there. But yeah. All right, so I'm looking for our last question here. Let's see. All right. So I guess the last question I'll answer is related to training on a GPU farm for high resolution and large quantities of photos. So as I mentioned, Jetson Nano, you can do the training for this project at a small scale on the Jetson Nano. But once you have a lot of data, or you're trying to process higher resolution images for training, you can definitely do this. Is the short answer. Is you can train on GPU clusters, and TensorFlow supports distributed training pretty well, I think, and PyTorch also has utilities for distributed training, I think. But my experience is mainly training on a desktop machine with a GPU and on the Jetson Nano itself. And yeah.
Okay, thank you all for attending today's webinar, and thank you, John, for presenting. You did a great job. There were a lot of great questions that came in that we weren't able to get to at this time, so be sure to post those on the forum and on GitHub to kind of keep the conversation going. We've recorded this presentation, and we'll have it along with additional resources available shortly on demand. You'll get an email later this afternoon with a link to that information. And don't forget to become an NVIDIA registered developer to have access to the latest news on products, software, events, and more. And thank you all for joining us today, and have a great day.
Thanks.